Hello and welcome back. We're continuing with our theme of illustrating our statistical lessons with abstract art from around the world, this time from Qatar. In the last chapter, we learned about central tendency, in particular, the mean score for a set of data. Now we're looking at statistics that help us describe variation in the data. Chapter 5.3, Variance and Standard Deviation. We talked about how the mean behaves under a linear transformation, and the mean is our star player for measuring central tendency. Now we're interested in standard deviation, our star player for measuring diversity. So, giving a nod to parallel construction and symmetry, we'll now learn how the standard deviation behaves under linear transformation. So let's review the definition of a linear transformation. Then we'll look at how the standard deviation behaves under a linear transformation, and then we'll look at a rationale. First, we'll review the definition of a linear transformation. A linear transformation includes adding, subtracting, multiplying, or dividing a number by a constant. These operations convert the original standard deviation to a linear transformation of the original standard deviation. The reasons we would want to perform a linear transformation of a dataset will become clear later in this course. At this point, I'll ask you to go on faith and accept my premise that this is valuable knowledge. This equation reads x star, or x transformed, is equal to a constant a multiplied by x plus a constant b. This equation provides the general form for any linear transformation of a set of numbers. How does the standard deviation behave under a linear transformation? Or stated more precisely, if the transformation of x equals a times x plus b, which we see here, transformation of x equals a times x plus the constant b, then the transformation of s, the standard deviation, equals a times s. In other words, a times the standard deviation. So this star is, we interpret that as linear transformation. So a linear transformation of the standard deviation equals the constant a times the standard deviation. The multiplicative part of the linear transformation, multiplying by 2, will affect the transformed standard deviation. The additive part of the linear transformation, adding 25, will not affect the transformed standard deviation. So here we're looking at if s equals 10 and the transformation of x equals 2x plus 25, then we want to do the corresponding transformation for standard deviation. It simply equals 2s. We don't have to worry about adding the additive part. So it's going to be 2 times 10. 2 times the standard deviation, or 20. It will be useful to contrast this to what we already learned about transforming a mean. As we learned in the prior chapter, when we transform a set of scores, the mean is impacted by both the multiplicative part of the transformation and the additive part. Here with standard deviation, we're only concerned with the multiplicative part. Now I'd like you to try your hand at computing the standard deviation of a little data set to give yourself practice computing the standard deviation, and also to verify the rule for transforming standard deviation and to find that it does in fact work. There are only 3 people in the data set. Each person has a score on a measure of well-being. Don's score is 40, Ellie's score is 50, and Fred's score is 60. Apply 2x plus 25 to make the linear transformation, and notice the original standard deviation is 10, and the standard deviation under linear transformation is 2 times 10, or 20. Take note of the fact that I didn't include the constant 25 when I computed the linear transformation of the standard deviation. So I just simply went from 10 to 20. In example 2, x bar, or average, of the dataset is 50, and s, or standard deviation, is 10. And the linear transformation of x is x divided by 5 minus 2. So that can be changed to 1/5 of x plus a negative 2. Then, recalling how we did a linear transformation of a mean, linear transformation of the mean of x equals 1/5 of the mean plus a negative 2, which is the same thing as subtracting a 2. So 1/5 of 50 plus a negative 2 is 8. And when we do the linear transformation of the standard deviation, it equals 1/5 of s, which equals 1/5 of 10, which equals 2. So remember, we only use the multiplicative part of the linear transformation. We leave off the additive part. Here we have Don with a score of 40, and x divided by 5 minus 2 is 6. Ellie has a score of 50, and x divided by 5 minus 2 is 8. Fred has a score of 60, and x divided by 5 minus 2 is 10. The standard deviation equals x, and the transformation equals 2. Notice I didn't include the constant negative 2 when I computed the transformed version of s, the standard deviation. So all of these transformations included the additive portion, which is the 2, because remember, negative 2 is just the same as adding, minus 2 is the same as adding a negative 2. But when I made the transformation on the standard deviation, I simply divided by 5 to get 2. So we need to understand the odd behavior of standard deviation under the linear transformation. Why does the multiplicative portion of the linear transformation impact the standard deviation, but not the additive portion? So may I mention again that in the prior chapter, when we transformed a dataset, the new mean score was impacted by both the multiplicative and the additive part of the transformation. So let's take a closer look and find out why the mean and the standard deviation are treated differently under a linear transformation. If we take a close look at the details, we see that this odd behavior of s, or standard deviation, under a linear transformation makes common sense. Imagine a data set we want to transform by multiplying each person's score by 10. Have we changed the mean? Yes, it is clear that the mean for the transformed scores in the right column will be different than the mean for the original scores in the left column. Have we changed the variability? Does the space between the values change? Have we moved the values apart or pulled the values closer together? Yes, with a multiplicative constant of 10, the values are now further apart from each other, and they span a larger range. So we can agree that multiplying a constant will change both the mean and the standard deviation. If we transform a data set by just adding a constant, does the mean change? Yes, again we can see that the mean of the scores in the right-hand column will be larger than the mean of the scores in the left-hand column. But does the relative spacing change? No, these people used to be 1 unit apart, and they're still 1 unit apart. The span or range has not changed, so it is clear that adding a constant does impact the mean, but does not impact the standard deviation. And here's a summary. We've already covered Unit 1 for Chapter 5. We looked at range and Q. We've looked at Unit 2 when we covered variance and standard deviation. We just finished Unit 3, linear transformations. Unit 4 is other properties of S. And Unit 5 is closing thoughts.